Welcome back. In this video, we're going to graph a few functions. And generally, when I approach graphing, I usually like to try either plotting points or identifying the parent function and using that approach. The first graph that we are going to draw is for the function f of x equals the quantity, absolute value, x plus 4 minus 2. And again, we can, it's pretty straightforward, so we can just plot a bunch of random points and see if we can determine a pattern and the end behavior. So we have x and f of x, and I always like to start in the middle with 0 because it's rather easy to figure out. X plus 4, so 0 plus 4 minus 2 is 2, and then we go in another direction. Let's make this 2. 2 plus 4, 6, minus 2 is 4, and then one more. Let's put 5. 5 plus 4 is 9, 7. So we've got pretty much a straight line going that direction. And then I like to do a few negative numbers to see if that works. Let's do negative 2. Negative 2 plus 4 is 2. Minus 2 is 0. And let's do negative 4. Negative 4 is 0. Minus 2. And so we have 5 points. And what we do is we end up graphing it, plotting these points, and seeing if we can determine a behavior. Okay? And this is x, and this is f of x. And so we have 0, 2, and we have negative 2, 0, and we have 2, 4, and 5, 7, and negative 4, 2. So we have actually a straight line in this manner, okay? And most of you know that an absolute value function is not a straight line. At some point it's going to turn. So from this point, you have to determine, okay, where is the turning point or the vertex of this absolute value function. And as it turns out, it's determined by these two numbers. The vertex is going to be negative 4, negative 2. And the vertex also means that you're going to have a horizontal and vertical shift. If you recall, an ordinary absolute value function starts at the vertex at the origin, and it goes slope of 1 in that direction, 1, 1, 2, 2, 3, 3, 4, 4, and a slope of negative 1 in this direction, negative 1, 1, negative 2, positive 2, negative 3, positive 3. This is the absolute value of x. So we need to take the function we have here and shift the parent function correctly. So let's go ahead and do that. Let's draw. Let's take our f of x axis and our x-axis. And let's, again, let's pick a point, 0, negative 2. 0, 4 is 0, positive 2. It's right here. And then our vertex is going to be negative 4, because it's the opposite, going in the horizontal direction, to the left 4 units, and down 2 units. So it's going to be negative 4, negative 2. Okay? So this is the vertex. Here's one of our points. So it's going to look like this direction. And going the other way, again, this is negative 4, negative 2. This is 0, 2. And if you notice, by the way, just a side note, this is 4 units this way up to 2. So if we go 4 units this way, it should go up to 2 as well. Okay, so this should be negative 8, positive 2. Let's check it. Negative 8 plus 4 is minus 4, but the absolute value is 4. Minus 2 is 2, so that is correct. And so let's draw these lines like this. Okay, and there's our absolute value function. Here's 2 points, and of course this point right here is one of the intercepts. This of course would be negative 2. Negative 2 plus 4 is 2, minus 2 is 0, and then the other one of course would be negative 6 right here. Negative 6, plug it in, negative 6 plus 4 is negative 2. Absolute value is 2 minus 2 is 0. And there you have it, an absolute value function taken by shifting it down 2 units and to the left 4 units. Now the second sketch we have is y equals 3 to the x minus 2 power plus 1. And of course this looks kind of bizarre. I don't know when we'll see this thing. But again, what I might do is I might plot a few points to get a rough idea of what's going to happen, or I might just skip that whole step and just go right to the parent function. Because what's going on here is this function is an exponent function. So it's very similar to y equals 3 to the x. And if we were to graph y equals 3 to the x, let's see what would happen. Okay, we would have, if x equals 0, the output would be 1. So 0, 1 is one of our points. Okay, 0, 1. If we put in x equals 1, we'd have 3. So 1, 3. And if x equals 2, 9. And you can see it shoots up rather quickly, exponentially. Okay, and then of course the negatives, if we put in a negative 1, it would be the reciprocal of 3, which is 1/3. So this would be negative 1, 1/3. And then to the negative 2 would be positive 1/9, and you see how quickly it approaches the asymptote of the x-axis. So this is what y equals 3 to the x looks like. So looking at that, let's take a look at the original equation we're going to sketch. It's 3 to the x minus 2 plus 1. So automatically we know, since this 1 is outside the function, we're going to have a vertical shift up 1, okay, which means this is going to be something like this, okay. And then the last thing we have to recognize is that this is x minus 2, so for every x value, before we do anything to this function, we're going to subtract 2 from it, which means we need to shift this thing to the right 2 spaces to have the same sort of outputs. So ultimately we're going to take this thing and we're going to move it over to the right, and it'll look something like this, okay, is what we're going to end up with, okay? So keeping that in mind, let's graph this, okay? Let's take, draw a new x and y axis. This is the y axis, and this is the x axis, x and y, alrighty? And again, our parent function looked like this, but we're going to shift it up 1, and we're going to shift it to the right 2. Okay, so what we will do is let's take our reference here, over here. So we know there's going to be an intercept right here, and this value is going to be 0. 0 to the negative 2 is 1/9. So this is going to be 1 and 1/9. And incidentally, by the way, actually before we even do this, let's draw our horizontal asymptote. Okay, if you recall, in the parent function y equals 3 to the x, we had a horizontal asymptote of 0. So since we've shifted it up 1, let's just make the horizontal asymptote of y equals 1. Okay, so we know that this function will never get below that. Okay, and of course our first value is, if we were to use positive 2, our output would be 2. So one of our points is going to be 2, 2. This is 2, 2. And here is 0, as we said, 0, 1/9. So basically what we're going to have is we're going to have something that looks like this and like that. Okay, and to clarify the graph a little bit, again, this is 2, 2. 3 to the 0 power is 1 plus 1 is 2. If we were to plug in 3, 3 minus 2 is 1, which is 3 plus that, so it's 4. So this is going to be 3, 4, and it's going to continue to go upward. This right here is 0, 1/9. And of course, if we plugged in negative 2 or negative 1, we would have 3 to the negative 3rd power, which is 1/27. So this would be 1 and 1/27, and continuing down towards y equals 1. Now the last function we're going to sketch is an absolute value function, or a form of it. It's g of x equals negative the square root of 5 minus x. And there's a couple different approaches. We can plot some numbers, or we can try to use the parent function. These negatives are going to make it a little trickier because we're going to have to do some reflection over the axes to adjust the function accordingly. So let's take a look first. First thing we want to do is, the first thing I'm going to do actually is I like to rewrite this, okay? Let's make this, this inside part negative x plus 5 instead, okay? I just want to do that to try to get this to look like the square root of x. And then one last thing I'm going to do actually is I want to rewrite this and make this negative square root of negative times x minus 5. Okay, so I think hopefully I haven't confused you too much, but I just want to demonstrate a point of reflection. So here's what we're going to try to graph, okay? And again, we recognize our first piece is the absolute value function. And if you recall, the absolute value function looks like this, okay? Here's some points I plotted. Negative 2's, negative 1 do not exist because they're negative roots and they're not real. So you start at 0, 0, then 1, 1, then 4, 2, and 9, 3, and extends out that way. Okay, so again, we go back to what we're working with. We have the square root of x. So the next question I would say is, what's x minus 5? Okay, and x minus 5, of course, is a shift to the right. So this is going to be, let's draw this. This is lightly. This is the square root of x minus 5. Okay, we shift it to the right. Okay, and now the next part is we have to take this negative and reflect it. And generally when you have a negative within the function, it means that you are going to reflect it over the y-axis. Okay, the reason is intuitively, let's take a look. If this is the square root of x, every value, this is 1, 1. To have the similar value, this is negative 1. So again, negative 1 becomes positive 1, 1. If this were 4, 2, and instead it became negative, you'd have to have negative 4 to make a negative negative 4, 2. So notice how it's been reflected over. If you plot points, you can see how obvious it is. Okay, so knowing that, let's go back to what we've got here. We have the square root of x minus 5. Okay, we took the square root of x, we shifted it over 5 units. Now we're going to make it negative. Okay, so in order to do that, we are going to basically take this and now go out that way. Okay, so this is the square root of negative x minus 5. I hope you're following me here. Okay, and so that's where we're at. And then the last thing we have to do is recognize that we have a negative in front of this whole thing. And again, when you have a negative outside of the function, it gets flipped over the x-axis. So if this is the square root of x, negative square root of x would mean every output here becomes negative. So you would actually have a graph that goes down that way. Okay, so what we basically got here in our original problem is we have a shift over 5 units, and then we have a flip to the left, and then we have a flip down. Okay, so knowing that, let's start from scratch. Let's graph the whole thing, and then we'll confirm it by plotting some points. Okay, so again, let's take our x and our g of x. So this is x, this is g of x. Okay, and again, we rewrote it. Negative square root of negative x minus 5. I hope that's not too confusing, but that's how we'll work with it. Okay, and again, we have a shift to the right of 5 units. So we have a shift to here, 5 units. Okay, and again, instead of going out this way, we are going to go out this way. Okay, for the negative. And then lastly, we have a negative outside the function, which means every output here has to be reflected over the x-axis. So our final answer should look like this. Okay, and now let's identify these points. This is 5, 0. That's quite obvious, right? And we'll go back to the original. Okay, 5 minus 5 is 0. So this is 5, 0. Okay, this right here, this value is 0 something. All right, and 5 minus 0 is square root of 5, which is a little over 2, but it's negative. So this is negative square root of 5. So we are going in the right direction, going down. Okay, and we can continue to plot a few more points. Let's do negative 4, because that would give us a clean square root. 5 minus minus 4 is 9. The square root of 9 is 3, negative 3. So that means this is going to be negative 4 -3, like that, -4, -3, and it continues on. So that's our final answer. So again, I did it from a couple different approaches. You might find something easier, like picking some points. But again, I always like to defer to finding a parent function and recognizing the shifts. These are the reflections, and this is the shift. And then I use some points to determine my dimensions. One last comment, notice the domain and range. The domain is all possible x values, which in this case, this radical must be 0 or positive, which means this x value must be 5 or anything less than 5. And then the range is basically, ordinarily it'd be all positive numbers, but in this case, since it's negative, the range is from 0 down to -infinity.